Okay, today we'll discuss amortized analysis, and particularly we missed Tuesday's lecture recording because the equipment didn't work correctly. So what I'll do today is I'll analyze two different problems, or I'll do an amortized analysis of two different problems to get a feel for what is the real purpose or what is the advantage of amortized analysis. So the first problem, by the way, I have now got a strange pain, so I'm getting used to it. Please bear with me. The first problem is so-called multipop operation. For stacks. So the idea is the following, that we know already stacks have two operations. First is push, that pushes an element onto the stack, and the second is pop, which pops an element from the top of the stack. Now we want another operation which is called multipop, and multipop, let us say, takes an argument n. This will pop n elements from the top of the stack. N elements from the top. Now the natural question to ask is what could be the complexity of the multipop operation? Well, if we consider the cost of a push operation as 1 unit, some arbitrary unit, but we have to do some work, and the cost of a pop operation also as 1 unit, then of course cost of multipop is n units. Which is not really very good, because consider this scenario. Suppose someone has given you a contract to write code for a stack, and that client wants you to implement three functions or three methods: push, pop, multipop, and also the client wants these methods to be as efficient as possible. So this would really not take much time. Now we didn't have any problem with push and pop because they take 1 unit of time, but when you implement multipop, that really blows up, because the client can pop a large number of items, and as the client increases the number of items, then the time for the multipop operation will also increase, as we have seen just now. Now, is it the true picture? So in other words, what I'm saying is multipop has complexity of order of n, when n is the size of the number of, or n is the number of items that you are popping. What amortized analysis tells us or helps us to do is to analyze situations like this, not in isolation of a single operation, but rather as part of a collection of operations. So what I mean by that? Now look at the client's perspective. I'm writing some pseudo Java-like code, but can the client write code like this? Suppose this is the client's main method. I am not writing everything. So can the client, starting with an empty stack, can the client write code like multipop 20, then multipop 10, and so on? Is it possible for the client to write code like this? The answer is yes. Of course, the client can write code like this, but starting from an empty stack, the client must have the corresponding elements or corresponding items pushed onto the stack. In other words, to be able to write this code, multipop 20, there must be at least 20 push operations before this. Why? Because unless you have pushed the items into the stack, onto the stack, how can you pop them? And multipop is basically a generalized popping, that is 20 items you are popping at the same time. So you can see why it is important to look at the context of a particular operation, because if we look at multipop in isolation, it looks like an order in operation. But if we look at why or how a multipop can be executed, then it doesn't look so bad. Why is that? Because let us say 20 push operations, 20 push. How much time it requires? 20 time units. And one multipop, how much time unit it requires? 20 time units again, because we are popping 20 times. So let us look at what is the total time we are spending. I mean total time for 20 push operations plus one multipop operations. It's 20 plus 20 equal to 40. And how many operations I am executing? I am executing actually total operations 20 plus 1, because 20 push operations and 1 multipop operations equal to 21. So what is the time per operation? Which is roughly 2. And you can change 20 to anything. In fact, to be able to write it, I can say to make it more notational, I can say that I execute C push operations and one multipop operation. So total number of operations is C plus 1, and what is the cost is C push operations will be C times, and one multipop which pops C elements is another C. So total cost is 2C. So what is cost per operation? Cost per op equal to 2C by C plus 1. For large C, you can ignore the 1 in the denominator, so it is roughly about 2. So we have generalized it. So you can see that what we are doing here is we are trying to understand in what context a particular operation can be used or executed. Unless 20 items are pushed on the stack, 20 items cannot be popped. And hence, to analyze the cost of a multipop operation, we have to really look at what must precede that multipop operation. So this is the first amortized analysis example.